So thank you, everybody. Andrea Barisani, you might have seen me yesterday in the NVIDIA talk. You might have not. So I'm going to talk here about the USB Armory, which is a project that we very recently announced and that is now in a crowdfunding phase. I will be super quick about it because this is a 1-hour presentation that we're going to squeeze in hopefully 25 minutes. So this is the device that I'm going to talk about, which is basically a computer squeezed in a very tiny USB stick. And it's all open source, and it's called the USB Armory. So why did we take on doing something like this? So we're a company that does security, so we wanted a very small trusted device for personal security applications. And as soon as we thought that it would be nice to have a computer in a very small form factor, a series of ideas popped up about having, enhanced mass storage with advanced capabilities, using it as an OpenSSH proxy, as a VPN router, Tor router, electronic wallet, and so on. And all of these applications fit the use case for having some hardware like this. So the first use case that we thought of was like, wouldn't it be nice to have enhanced mass storage so that not only I can copy a file on a USB drive, but it would also get automatically encrypted with whatever key that you might want to, with a key that maybe it's selected upon the folder that we're placing the file on, or the name of the file, or whatever criteria that we might decide. So something that would have the flexibility to be changed in the manner that you please. So not a single purpose fixed hardware for doing something like this. And if we have a computer on a USB drive, we could also maybe scan the file for viruses, malware, whatever you like. So this was one of ideas. And the way that we wanted to implement it was to have a tiny Linux computer emulating USB storage and then filtering the files that you copy on it to whatever filter that you might want to have. And then, of course, once this idea came up, we thought, but we could do so much more. Let's, if we have a small device, which is actually a computer, we could just use TCP/IP and then have capabilities such as uploading the files somewhere, sending it over email, wherever you want to, giving you a Google Drive, but Google might be a very bad word here for this audience, so whatever file sharing or direct upload mechanism that you want. So all of these possibilities enabled by the fact of having a simple computer, open computer on a USB drive. And then we thought, but we could do so much more. What if for deniability, you could have it wipe itself automatically if a failsafe word is detected? You copy a file on it, which is a very specific name, or you create a folder, which is a very specific name, or you do whatever action that you might want to do, and then the drive automatically wipes itself. All of these features are, of course, things that you cannot achieve nowadays with a normal USB drive or any commercial product that is out there. So, and you can see the thought process. As soon as we had this idea of having such a tiny form factor for an open source design, all of these possibilities came to mind. It, of course, can be used as an SSH proxy. So imagine that you are on an internet kiosk or using a computer that you don't trust, and you want to SSH to your servers from it. You connect this USB device onto your laptop. It gets exposed with TCP/IP. You SSH to it with maybe a one-time password or whatever you might want, or a password that you don't care if it gets compromised. And then from it, you SSH out to the internet by using the private keys, which are stored on the device, and that they do not leak on the host computer, which is supporting the device for communication. It can be used as a password manager. Why not? Either something really stupid where you use a PIN, you unlock whatever web application that you have on it, you ask for a password for a specific site, the password gets copied to your clipboard, or it gets displayed, or you can even have a proxy on the device itself, a web proxy that would just replace whatever magic placeholder for a password that you're putting with the actual real password that then never gets compromised on the USB host. So all of these various applications are enabled by having such a very simple concept of having a computer on a USB drive. And of course, it can also do the standard role of being used as an authentication token with UTF, U2F, the FIDO protocol, which was recently announced, the Google authentication token, or any other token that you might think of course. And there's also a very interesting idea, which now can be done with such hardware, which I really, really like, which is authenticating the host. So the USB device authenticates the machine that it is connected to. Because of course, being this now an active device with its own kernel, its own applications that can be executed and scheduled as you prefer, this device can communicate with your host and can decide to assess if the host that's being connected to is the legitimate one or not. A very simple mechanism would be just to check the SSH fingerprint for the SSH daemon that is running on your laptop. And then, of course, you can decide what action to take if the host is not trusted. The device can decide to wipe itself. It can decide to even brick itself because the specific system on a chip has way to fuse keys that if they're random, then the system on a chip would never be able to boot any other code. So all of these possibilities are unthinkable with standard USB devices, and especially this one is something that I really like. You can even have it so that if this device is connected to a laptop which is not yours, it will not do anything particularly damaging, but it will just present a different set of files. Why not? I'll plug it to your laptop and you see Mickey Mouse. I'll plug it to mine and I see porn. I don't know, you can decide, whatever you like. So in order to support this application, we have a few design goals. It needs to be compact and USB powered. And when I mean USB powered, I don't mean to have a power supply with a USB form factor. I mean being powered by a standard USB port on your laptop or on your PC. It needs to have a fast CPU, not some very slow single-purpose microcontroller, which of course might do some of these use cases, but it would be highly optimized the code in order to achieve your goals. We wanted something which is fast and a generous amount of RAM. We want secure boot. We want to be able to sign with our own keys the code that runs on the storage of this device, and so that it gets executed on my personal or your personal device. Standard connectivity over USB, and very important to have a familiar developing and execution environment. So not something which is heavily customized, not something which is hard to develop, something that it's easy, super easy. And of course, it needs to be open. Open software, open hardware. This is a security device, and one of our goals is also to minimize supply chain attacks. So you need to be able to look at this device, to open schematics and see exactly what's here. And if you want to modify it, you want to have the PCB layout, we also provide that. So the challenges, the first of many challenges in doing something like this was, of course, selecting the system on a chip. And we went for the Freescale IMX53. Why did we choose the IMX53? It's powerful. It's an A8 ARM CPU. It can be clocked between 800 megahertz and 1.2 gigahertz. Almost every datasheet and manual is public. No NDA required, especially for secure boot, which was very important for us. I wouldn't go as far as saying that the datasheets of Freescale are awesome, because they're not, but they're less scrappy than many other vendors, which is fine by me. He has ARM Trustzone, secure boot, secure storage, and secure RAM on the system on a chip that we can leverage on. There's a detailed power consumption guide available, which to us is very useful when we want to prototype such design. And there's excellent native support. This system on a chip can run Android, Debian, Ubuntu, FreeBSD, the Gnode OS, a lot of different operating systems natively with no customization required, which of course saved us from a lot of effort in customizing things, but also empowers you to just use stock Linux distributions on a USB device. And also this specific system on a chip is a good stock and production support guarantee, because you don't want to commit to a design and then find out in 1 month that, oh, sorry, we don't have this chip anymore, because of course that's going to be a nightmare. I'll skip over this because we didn't have too much time. One of the things that we evaluate is having a good Trustzone support into this CPU, which will allow us to separate the software that runs on this device to even have a further level of separation. So of course, with this device, we shift the concept of live OS. This is not just a storage where you boot from. It's a completely independent computer that runs. But what we can do, we can segregate the code that runs on this device even more, and having the so-called normal and secure world that Truston supports. And these two worlds are completely separate. And the interesting thing about Truston is that not only you can separate something like the memory space and the code execution segments, but also all the different hardware subcomponents which are attached to the system on a chip can be assigned to one of these two worlds. So just to give you an example, there's an LED on this device, and this LED, if you want, can be assigned solely on the secure world, which means that whenever the LED is on, you know by design, by hardware enforcement, that at that specific time, the secure container is running and not the normal one, just by looking at an LED. And we thought that's a very cool feature. So in this way, one of the ideas that we have is to implement the encryption and decryption for the micro SD card in a secure container. So that even if the Linux OS, which is a, of course, wider attack surface, get compromised, you won't be able to extract the encryption keys from memory, because that memory cannot be accessed either by direct addressing or also by doing DMAs with the other components on the system on a chip, because every single component is Truston aware. So this is a development timeline that we did. We had a concept idea in January based on a completely different system on a chips. In March, we began development. We did a breakout board. In August, we ordered an alpha board. The alpha board worked right away. We announced the project in October. In November, we made an order for beta boards. The beta boards arrived, and from there, we finalized the design for the Mark I. Completely open source, open hardware. It is crowdfunding right now on crowd supply, and we're 72% of our goal. So I'm pretty sure that we can make this happen. But of course, if you're interested into this, please check that. So it is USB horsepower, very small. He has a micro SD card slot. So all of the codes and the bootloader, they boot from the micro SD card. There's a 5-pin breakout header for GPIOs, SPI, I2C, and serial, which you can use. There's the LED, which can be used for secure mode detection. We tested already Ubuntu and Debian and Android and Genode OS running on it without any issues whatsoever. And we also tested that we can emulate Ethernet mass storage, input devices, pretty much everything. So, of course, so far I only mentioned device mode. And while developing the device, I would say we were a little dumb, because we drove the ID pin from the USB on the go to ground. And we thought, you know, we can never change the role of that device. But it turns out that we can also put the device in host mode. So by putting the device in host mode, it means that if you have a female-to-female adapter, which here it's implemented with a breadboard, you just plug a keyboard, a mouse, a USB screen, a USB Wi-Fi adapter, and you can use this in completely standalone mode, just by a software configuration. And then you can decide to pull it off, put it in device mode, and attach it to your laptop, which I think, you know, it's a very nice way of inverting its use. So for the super paranoid, in this way, it's completely standalone. And this is the custom host adapter that we're making. Of course, all of you hardware nerds and geeks can make this very easily on a breadboard or whatever. It's super easy, but it's simply female to female, and then a micro USB for power. So with just a power USB hub and this adapter, you can use the device with whatever peripherals you want in host mode. So what were the challenges in making this device? Of course, we have BGA chips for the system on a chip and the memory. And it's also a very tiny form factor, which means that there was no way, at least we were incapable of doing, maybe some of you are much better than us, to prototype this by hand, to just order the PCBs and solder everything on our own. So the process was, we make a design, we make the order for 2 10 devices, very expensive one, because it's a high specifications PCB, and then we hope for the best. And the other challenge, and then the first thing that we wanted to do was like, let's try to be smart, let's try to avoid this, and let's do a BGA prototyping board. And our idea was, we make a really expensive board and we buy a really expensive socket adapter, which is there, which allows us to clamp the system on a chip without actually soldering anything at all. It's about a 700 euro adapter. And maybe this way we can power it up and test pretty much everything except the memory and test all of the possible routing and configuration without, wasting a lot of money with PCBs. So, and this is the power boards that we tried to make. But Darth Vader there, which is me, killed the Admiral, which is my colleague, because it was something like, you failed me for the last time. Because after making 10 of these, we would never manage to make them work, because the tolerances for distances between the inductors and capacitors and the power control unit are so high that by doing this by hand, as much as careful as you can be, out of 7 voltage lines, 1 of them will not be stable enough. So this was definitely not the right way of doing things. So this thing turned out to be like the Superstar Destroyer, a giant thing which costs a lot of money, it's slow, and at the end of the day, it's useless. So don't do this. If you're making hardware, go for the proper design right away, because if you're lucky, like we were, it will work the first try, and you can save a lot of time. So when you have switching power like this, don't. At least in our case, it was a completely pointless exercise to try and be smart. Second challenge, we use KiCad to do everything, which is a nightmare. I mean, it's open source, and we wanted to use it because then you can open up the design and modify it. But routing RAM with KiCad is, I would really rather be in a different life. It took me 2 weeks to route the RAM between the SoC and the memory module. So that was a real pain. But we made it, it works, so it can be done, and I think it's pretty amazing that you can do it completely with open source tools. The reason why RAM routing is tricky is because all of those lines need to be exactly of the same length if you really want to be super, paranoid about it. And when your PCB costs a lot and you don't want to, waste money, you really want to make sure that they are the same length. And KiCad doesn't help you in doing that at all. So then you go from the schematics, but KiCad is very good in giving you 3D representations, by the way, of the board, which is not that useful, but, at least it looks nice. So we see our 3D thing, we get hyped, and then we make the order, and we get the alpha board. And the alpha board, you see the Admiral, it's a different one than the one before, because that one died, but they all look the same anyway. So that Admiral is alive and standing because the alpha board worked at the first try. Again, I would really inspire you to make hardware, and even if it seems like a very daunting task for certain designs, this is one of the most difficult things I could think of making, chances are that you will be successful. So I really want to inspire you into doing hardware. So the alpha board was a little larger because we wanted to have a JTAG connection and all possible test points to figure out what was wrong in case things went wrong, because it could be really, really difficult to debug issues, especially when the board doesn't, it doesn't power up. And also you have to work with the manufacturer a lot, because doing a design on KiCad, and even if your design rules pass, it doesn't really mean that you can manufacture that board reliably on a larger scale. So it was really important to work with the manufacturer to understand what were the tolerances of the pick and place machine, the soldering mechanism, to understand what were the various tolerances and see if the board could have been produced. Also because when you make something of this size, you're going to violate pretty much every single recommendation that you find on pretty much every single data sheet for every single component. They will tell you, oh, you should do this. And then you're like, oh, you asked me to have like a soccer field, like miles of traces around the memory, but I can only go that way. So you will forget all of that and you will just go for it. But it works, We had JTAG, which was useless, but it makes a very nice picture because that also works. And you can connect to it over serial port with a bus pirate. Power consumption was great. It works. We can turn on the LED, which we added later, by the way. And the same power of a Pentium 2 is squeezed right there, which I think, and it's all done with open source tools. I think this is amazing. And anybody can do this. Thank you. Then we get the beta boards. So beta boards, we order 6 revisions actually 1, 2, 3, 7 revisions to lower down the price. So we tried different things. We tried to move from 8 layers to 6 layers. We ignored a few recommendations about how to power RAM up. We removed certain components. We tried not to power the USB host, which at the end we didn't do, which is a good thing because now we also have host mode. So we went from alpha to beta to Mark 1, which is the final design. And the betas, as you can see, were different iterations. So that was one order with multiple designs. They all worked, but from there, we picked one. We picked the one that was cheaper and that was most effective. Lessons learned, number 1. There were some tiny inductors which were extremely fragile. And when I say fragile, I mean that after 1 week, they were just coming off. And not because the soldering wasn't done correctly, that you will never break unless you do it intentionally, but because the component itself wasn't meant even to take the shock of being placed on a table like that twice a day for a week. They were coming off. The importance of testing, test. You don't want to make 1,000 boards that have this problem. So one of the first things that we did, we changed the inductors with new ones, which have a very nice shape, which looks like Battlestar Galactica notepad, so I'm really proud of them. When you do hardware, you will get super hyped about these things. You're like, oh, I'm reading a datasheet about ESD, it's 50 pages long, it's awesome, just for one tiny component. Don't do it, you get crazy. Second, very evil problem, gold plating. We need gold plating for the USB connection because otherwise, after 50 uses, it would just not work anymore. The way you do gold plating, we don't do gold plating. We just tell to the manufacturer, do gold plating on those pads, and then we'll do it. And the way they do it, in this case, in the beta version, they need some contact points to place the deposit. And what they did 4 traces that you can see there that were going outwards over the edge of the board. So what happened there? We plug the board, we see that we have a 5 seconds of delay, and then the boot starts every single time. And we're like, where are these 5 seconds coming from? So what are you going to do? You search into every datasheet, and you search with your PDF reader 5 seconds. And you find that 5 seconds is the wait time that the voltage regulator uses for under voltage detection. And then we're like, so why do we have an under voltage on connection? Because by cutting the board, we have 4 little conductive dots that make contact with the USB plug, then no contact, and then contact again. And that causes the under voltage at connection. We didn't design those traces, the manufacturer did. And we spent 3 days banging our hands trying to debug this problem. So that was very evil. And on the right side, you see a better way of doing gold plating with the 4 little, pads on the traces. So that was lesson learned number 2. Even things that should be trivial, options that you just click, oh yeah, sure, do gold plating, they might result in bugs. So this is the final design. We moved JTAG on the back for people that still want to use it by soldering those pads. JTAG can be disabled, of course, and when you are in secure trust zone mode, of course, you will not be able to use it, so don't worry about that. And we see the pin header on the left side, and I have exactly 6 minutes for question. If you're interested in this project, please go on the crowdfunding page. Thank you very much. And actually, I totally forgot. I have one attached to my laptop, and I can just SSH to it. So this is my USB drive running Linux. And this is the Electrum Bitcoin wallet running on the USB drive and being exported over X to my Windows machine. So all of the keys are on the drive. This application took 30 seconds to test. As soon as we put the device, we're like, let's do that. So you can see the potentiality of this platform. Thank you. Questions?
Question from microphone 4, please.
First of all, thanks for making such a great thing. And second of all, I'd like to ask if you have already an alpha or beta software for authenticated boot.
For authenticated boot?
Yes.
Okay, so the secure boot, there is an application note by Freescale, which we're gonna convert into open source scripts where you can just use them. So secure boot is there. It's not something that we implement, but we're gonna make it easier for you in order to use it. So, and that should happen before March. Now we wanna push the hardware out, but then we're gonna make that.
Awesome, thanks.
Microphone number 2, please.
Thanks, great project. And there is an SD card with Wi-Fi on it and full Linux system running it, and it's kind of open source with unit booting. Did you take a look at this? And what's
the name of it?
It was Wi-Fi or something from SanDisk, if I remember correct. But there are 2 versions of it. And you can run your own code on it. You don't have the nice debugging features, but you can. It's used for sharing files over Wi-Fi for photographs.
Right.
Photographers, and you can manipulate the file system as well. But it has less features, so this is great. But did you take a look at it before you did this?
So before we had the idea, of course, we looked at everything that was out there. And there was nothing that fit all the features and nothing that was open source like this. And also, you should be very careful because some of them, they will draw more than 500 milliamps in order to use the Wi-Fi and HDMI and the CPU. So one thing is having a power adapter, which is a micro USB form factor. One thing is being power from the USB host completely. Okay, so that's a key difference. So none of these qualities were existing when we started this project, and I don't think they exist now still. So this, in my opinion, is unique.
Okay, yes, thank you. Thank you.
Microphone number 5, please.
Hey, do you have experienced any heat problems? And the second question is, could you imagine to put a robust casing around it such that it can be attached to a key ring and be carried around every day?
So we're working on a case right now, and we hope for a case option to be available on crowd supply before the end of January. So we're definitely thinking of that, but it's also open source. So if anybody has capabilities for making a case, you can do it. Regarding heat, we tested it, of course. If you're using CPU 100% and memory 100%, it gets toasty, but it won't damage the board and it won't damage you unless you're extremely stupid. So it gets hot as any naked board and any sock, but there's not a problem at all about that, and we tested that.
Microphone number 1, please.
Hi, thank you for the great work. My question is about, you told us that this is all open source, and now as far as I know, the trust zone with ARM, you need to sign with them an NDA.
No, that's not correct. Every reference guide and usage guide for trust zone is public and can be used publicly. Actually, the support for trust zone, there are 2 different aspects. There's what ARM gives you in the instruction set, which you will find in the ARM assembly instruction set, where of course no NDA is required. And then there's the hardware support, which is vendor dependent. The hardware support, which is vendor dependent, is only partially under NDA, but all of it is published within the Gnode OS source code. So all the information that you need to use trust zone is open.
Okay, great. Thank you.
Thank you.
Microphone number 3, please.
Hi, thanks for the great project. Quick question. If you're going to use it as a standalone computer, it would be really useful to have HDMI at some point. I mean, obviously it's open hardware, but I wonder if you thought about it.
So one of the things that you want to be careful when you make hardware, you don't want to put too many features on it, because otherwise you're going to derail. We like minimal, beautiful designs. So we didn't think of HDMI for a second. Thank you. And guess what? We realized that by taking the inverse path, we can use USB host mode, and you can use a USB monitor. Of course, it's not like HDMI, but you can still, if you want to, use it completely standalone without all the hassle of having an HDMI connector. So I don't want to enter into the area of HDMI sticks that are for multimedia purposes. I want this to be focused on that. But who knows, maybe in the future. And it's open source, so if you want to add a connector, just take the project and do it. Thank you.
Thanks.
We can take one last question. Microphone 2, please.
Okay.
If I got that correctly, I can put my own keys on the device for verifying the software that's running on it, right?
Yes.
So how does that work exactly? How can I put my own keys? Does it work via USB? What does prevent a malicious attacker?
So you bootstrap, so you can do it from either the bootloader or from Linux itself. You can fuse the keys. There are certain registers which you can use, and you don't fuse the keys, you fuse the hash of the public key. You have 4 slots, and you can also have 1 revocation key, I think, I don't remember, but you can have up to 4 different keys, and those are yours. And once those are enforced, the bootloader needs to be signed with those keys, okay? If you, otherwise, nothing will boot, and there's no way to override it.
Okay, very cool. Thanks.
Thank you, Andrea.
Thank you very
Please give
much.
Andrea, a warm round of applause.